All right, so this is your first full truss calculation. Follow along as we go. This is a pretty easy truss, but it's harder than the one you're going to do on your own tomorrow. So I want to go over this, and this is like the process you use on every problem. I said it before that every truss is different, but our process can kind of be the same. Like step one, you should always determine if your bridge is statically determinate, which means does 2 times j equal m plus r. Okay, that should be your first step every time, because if that's not true, you stop the problem. So let's go ahead and do that right now. I want to check on this problem. I have 1, 2, 3, 4 joints. Okay, so 2 times 4. Does it equal, I count the beams, 1, 2, 3, 4, 5, plus my reaction forces, and I might as well draw these in as I go. This is a roller, so there's a reaction force on joint C in the y direction. Reese. I've seen Reese before, he's our buddy. Okay, and over here, good old Rax and Ray are going to show up because this pin joint will be holding it up, so R, A, Y, and A will have a horizontal on it too because it's pinned in, so the bridge doesn't roll away. So it's Rax and Ray. So I have 3 reaction forces, and yes, 2 times 4 does equal 5 plus 3. So I'm doing the problem. Now, use equilibrium equations to find the external forces. This is basically what we've been doing in our practice so far on worksheet 1 and worksheet 2 at the beginning of worksheet 2. That's where we're finding the moments clockwise must equal the moments counterclockwise. And then your forces up must equal your forces down. And your forces left must equal forces right. So it's basically all the external things we did before. So let's do that. Let's go ahead and try that out. So down here, I like to organize my work. So number 1, I'll put here, because you get points for everything you do. If I check it statically determined, I'll get points for that. If I can do my whole thing with the wrenches, then I'll get points for that. So I want to check, did the clockwise and counterclockwise cancel each other out? So if I put my rotation point here for my wrenches, I can easily see there's one down force that's trying to rotate my bridge this way. So I got my wrench pretty much looks like this. And that pink wrench with a 1,200 pound force, so it's a very small car like a Honda Fit from Hanslick, is trying to rotate my bridge clockwise. So I'm going to go ahead and write that's a 1,200 pound force times its horizontal distance because it's a vertical push. So its distance is 10 feet. And that has to equal the counterclockwise rotation. So here, I'll use yellow. If I imagine this force pushing up, I got a wrench that goes like this all the way here. Okay, and that is trying to rotate my bridge up into the air. Okay, so I got one force that's trying to crank the bridge into the ground, the other one going up in the air, and that is RCY, I don't know it yet, times its distance. Now don't fall into the trap and write 4, because you want its distance to the pivot point. So it's actually going to be 10 plus 4, which is 14 feet. Then we can do a little division, and you should start to feel comfortable with these type of problems with the wrenches and stuff. The feet cancel with feet, so I'll be left with pounds. And this is where we're going to use these answers to take it one step further in a second. So 1,200 times 10 equals divided by 14 feet. And we get 857.14. 857.14 pounds. That I'm going to write up here. Okay, that's helpful. Now, my ups have to equal my downs, and my lefts have to equal my rights. So it's still in step 2, but I'm going to say force up must equal force down. All right, let's see how this works. I have 1 down, and I have 2 ups. So my 1,200 pounds, my force ups. So I have Ray and this 857 must equal my 1 down, 1,200 pounds. So I do a little subtraction, and Ray must equal 1,200 minus 857.16 pounds, and we get 342.84 pounds. 342.84 pounds. Awesome. Okay, and then my lefts have to equal my rights, which is really quick. Okay, so my force left has to equal my force right. I only see RAX as a right force. I don't see any other forces for left, so there are 0 pounds going left. So Rax is 0. I got all three reaction forces. Awesome. That wasn't even that bad. Okay, you put those on the picture when you get them. So now I don't have any unknowns. Those are all my external forces. Now we're going to take it a step further, because you should already kind of know how to do that. We're going to take it a step further and find all the forces on the beams. This is big time, man. Big time. Okay, but before we do, I'm probably going to do step 3 and 4 in this video and then switch over, because step 5 is like where most of the work in these problems is. This is like, I think of this as like prep work. All the first 4 steps are just getting the problem ready. After that, then the real fun begins. Okay, so I like to keep my work organized, so there's step 2. Step 3 is find all the angles on the base. So I need to know this angle. I can assume 90 degrees on here. You're allowed to do that. If it looks like a 90, we'll assume it is. I need to find angle A, and I need to find angle C. Okay. Now, good old trig helps you do that. We just did a practice problem on our warm-up sheet, right? We did, if you ever want to find an angle, it's basically the inverse tangent of y over x. That's going to be our shortcut. So find the angles, right? So for angle A is going to equal the inverse tangent of the y over the x for that triangle. So if you look at this triangle, look at the right triangle, see this guy, ABD. What is the y? It's this height, which is 6 feet, over the x, which is 10 feet. So I can just do inverse tangent of 6 feet over 10 feet. If my calculator is in degrees, I'll just do inverse tangent of 6 over 10, because the feet cancel. And we get 30.96. Let's call it 40.0, because it rounds to that. 40.0 degrees. I'm going to do the same thing for angle C. So I look at angle C, and I set up my equation. I'm going to say angle C is the inverse tangent of the y over the x. I would just write myself a reminder here. Y over x. So when I look at this angle, its height is still 6, but its base is 4. Okay, so it's going to be a different angle. So I have 6 feet over 4 feet. Okay, and the feet cancel again. So I just got to type that in my calculator. Inverse tangent of 6 over 4. And I get 56.3 degrees. Okay, awesome. So step 3 is done. Now I want to put those on my picture. I want to write 40.0, and I want to write 56.3 degrees. Those are the only angles we need. You never ever need the angles up top. You only need the angles formed with a base, which is kind of cool. It goes back to a geometry concept that we'll talk about later. Now, step 4 is draw a free body diagram. Now, I did this while I was gone. We call it FBD in the future, so we don't have to write as many words. So this is step 4. Draw a free body diagram. Now, we did this with like a sled, and we did this with pushing a refrigerator up a hill and stuff like that. But what the good thing about this is free body diagrams are so easy to draw if you do it in pencil. Because I just get to draw this bridge without the pin and the roller and the forces on them. And if I have an eraser, it's really easy. Okay, so let's redraw this bridge. Now my pen is erasable, so that's why I'm doing it in pen. So I'm going to try to redraw this bridge. The measurements don't matter anymore as much. Well, that's all right. And then you got this straight down thing here. Okay, so I'm just redrawing it. I'm going to label A, B, C, and D. Okay, so we label it, and then put your reaction forces on. So I got this force going up at 342.84. Okay, I got a force here of 857.16. Put pounds on there. Okay, and I don't have to write the 0 on there. It's kind of excessive. If you have 0 force, you really need to write it. And I have this 1,200 pound external force on there too. So those are the only forces happening on my bridge on the outside. The 0 I don't have to draw. So now, to make it a free body diagram, you just erase the middles of every one of these beams, because we're going to be looking at each joint on its own. So I'm erasing all the middles. This is why you do it in pencil. It really helps you focus on each joint at a time. This is called the method of joints, the method we use. Now, here's where good old common sense comes in, because all of these need arrows. But I hope you understand this, so pay close attention on the next minute or so. I actually know which way the force is on here. Is it going up or is it going down? And you know how I know? If this bridge is not moving and I have an up force, the only thing that can keep joint A, and remember, we get to ignore all other joints. The only thing that can keep joint A from floating into the air is if there's some sort of down force fighting that. Well, the only way to make a down force in this whole picture, see how that's left and right? The only way to make a down force is if that force is pushing down. Now I have a down and left force, so guess which way this force has to go? The only thing that can fight this left force and keep this joint A from floating off to the side must be a right force. So I'm going to draw a little right force. Okay, and now here's a cool thing. In science class, you learn that every action has an equal and opposite reaction, right? Force. So if I'm pulling, imagine this is beam AD. If I pull to the left, down and to the left on it, what do I have to do with my right hand to keep my pen from moving? Okay, right now, if I don't do anything, it just pulls off. But our bridge isn't moving, right? So this down force has an equal and opposite up force. It's like it's already done for you. And if I'm pushing, see this is pushing. If I'm pushing with my left hand, it would move. But my bridge isn't moving. So there must be a force that's fighting it over here, an equal and opposite force. And that's kind of cool, because now it's like a domino effect. Okay, think about it. Now on joint B, I ignore joint A for a second. If I have a left force, there must be a right force to fight it. If I have a down force, there must be an up force. So you're figuring out all these arrows without even trying very hard. Same deal here. Look at joint D. If there's an up force here, there must be a down force. On joint C, if there's an up, the only